On assiste aujourd'hui à la soutenance de doctorat de mademoiselle Wordة العقون pour obtenir son diplôme de doctorat. Donc, Wordة العقون est une doctorante au sein du laboratoire de physique de matériaux à l'université de Galma. Le jury est composé de moi-même, le professeur Yahya Hakima, président du jury, de monsieur le directeur de thèse, monsieur le professeur des examinateurs, monsieur Mouraji Hussein, professeur de l'université d'Annaba, monsieur Baziz Hakim, professeur de l'université de Msila, et madame professeur Moumi Hayat, professeur de l'université de Galma. Donc, mademoiselle, on vous laisse le temps nécessaire pour nous exposer l'essentiel des travaux. Vous pouvez commencer et bon courage.
Thank you so much, Your Honor. Bismillahirrahmanirrahim. Honorable President Madam Yahi, respected jury members, Professor Baziz, Professor Miraji, and Professor Mouni, esteemed supervisor, co-supervisor, and our guest of honor, Professor Fatih from the University of Aden, and distinguished audience, perfect afternoon to all of you. First of all, I extend my sincere gratitude for your presence here today. Thank you for choosing to spend the next 2 hours or so with me talking about what has been my driving passion during the last 5 years. I hope it will enlighten, entertain, and prove worthy of acceptance. Thank you so much. So my dissertation is titled Ab initio study of the properties of 3D SRS-based monodoped and codoped compounds, a comparative study of the 2D and 3D monodoped compounds. This work of dissertation was realized under the supervision of Professor Adnan Madour and co-supervision of Dr. Shahrazad Bouris from our University of Rumi 1945 Galma. Before diving into the depths of my dissertation, let me provide you with an outline that guides through exploration of the intricacies of my research. So the dissertation presentation begins with an introduction, followed by a comprehensive literature background. Moving forward, I will present the theory and computational techniques. The results and discussion section will then dive into the intricacies of these findings. And finally, I will conclude this academic journey by a conclusion and future perspectives, followed by some references. Well, imagine a world where electronics are faster, smaller, and more efficient. A world where information storage is dense, our renewable energy is readily harnessed, and renewable energy also enhances to the tune of our technology. This is the world promised by spintronics, a revolutionary field that has harnessed the hidden power of the electron spin. So in this dissertation, we will delve into the fascinating world of spintronics. We will explore why is it of interest, how does it work and why, how is it produced, and what devices are used. As it is known, most technology is based on electronics that uses the charge to manipulate encoded information. The charge degree of freedom of the electron can be easily manipulated by using an electric field. In conventional computer memories, such as random access memories, information can be encoded using two distinct ways, either logic 0 or for false or logic 1 for true. Spintronics uses another degree of freedom called spin in addition to the charge. The electron assumes that the spin has two orientations, either up or down, resulting in a spin current. If all the spins are oriented in the same way, we can say we have magnetization and it is logic 1, else it is logic 0. Spintronics has garnered a lot of attention, which is evident from the increasing number of publications per year, using the search case Spintronics from Dimensions database. Interestingly, in 2092 alone, more than 40,000 publications were published, which means over one paper per year. Recently, the scope of spintronics has been extended to envelop not only the spin flow, but also the heat flow in new domain called spin calitronics based on thermoelectric materials. Also, the principle of light is added to complete the diagram. How we created our materials that are applicable for spintronics, spin calitronics, and optoelectronics simply by combining elements from the table periodic of elements basically the binary SRS from our group 26 family to create various random and innovative structures throughout using different processes, namely doping with iron, co-doping with iron and alkali metals, and reducing the dimension of the monodoped compounds to monolayers. Key components for spintronic applications are the dilute magnetic semiconductors that could be defined as host non-semiconductors, magnetic, doped with magnetic dopant ions, especially that have the half-failed 3D shell. So when a charge current is passed throughout two electrodes, only the spin-ups are injected into the magnetic materials, resulting in 100 spin polarization. On the other side, 2D monolayers are materials that could be defined as materials that have two dimensions at the macroscopic scale and only one dimension at the nanoscale. A prototype example of this category of materials include the single atomic thick graphene. What characterizes this category of materials from their 3D bulk counterparts is their high surface to volume ratio, and the confinement effect is more pronounced. Also, this category of materials has begins to increase it and gathered a lot of attentions, which is evident from the increasing number in publications per year. Interestingly, in 2092 alone, more than 100,000 publications were published, which means over 5 papers per hour. The binary SRS used in our study, in its bulk form, has a Ruxal type structure, a symmetry group number 225, an experimental lattice parameter of 6.059 angstrom, and a direct wide band gap in the gamma X direction of 4.32 electron volt. In its monolayer form, it has an hexagonal type structure like a graphene, a symmetry group number 187, and a theoretical lattice parameter of 4.85 angstrom, and a direct band gap in the M-gamma direction of 2.77 electron volt. The aim behind using iron as dopants, because they are one among the 3 ferromagnetic materials with high Curie temperatures and high magnetic moments. Also, they are good conductor for electricity and one of the most abundant elements on Earth. Also, they have high temperature and high tensile strength. On the other side, why alkali metals as co-dopants? Because they are non-toxic elements and one of the most abundant elements on Earth. They are best dopants for thermoelectric applications and behave as donors and hence could enhance electronic and magnetic properties. We move to the theory and computational techniques. So classically, determining the properties of any computational systems could be defined by solving the Schrödinger equation independent of time as follows. So the Hamiltonian of the system consists of the contribution from both kinetic and potential energy terms. That contains the kinetic energy electrons and kinetic energy of nucleus, the nucleus electron attraction, electron-electron repulsion, and nucleus-nucleus repulsion. Unfortunately, the solution of this equation remains impossible due to the large number of interacting particles. So the density functional theory comes to fix this problem by reducing the number of dimensions from 3n to only 3 and taking into consideration the electron of density. But how to solve? Cohen and Sham showed finding the right electron density involves solving a set of equations, each having this formula, in which the most important parameter in this equation is the potential of exchange correlation, which is a known quantity and needs to be approximated using different or similar exchange correlation functionals, namely local density approximation, generalized gradient approximation, MBG or HSE functionals. The aim of the DFT is the numerical solution of the Cohen-Sham equations through using different processes. Through different software packages such as VN2K or VASP as used in our case. So VN2K is a code based on FPLAPW, and within the Maventin spheres it takes both the core and valence states into consideration. In the interstitial region it takes only the plane waves. on the other side, is based on pseudo-potential, and within the Mafeltin spheres, it takes into consideration only the valence states. In the interstitial region, a plane wave basis set is used. Both the codes uses periodic boundary conditions and are Prometheus software packages and can calculate different properties, including structural, electronic, magnetic, optical, thermoelectric, etc. We move to the most important part of our presentation, which is the result and discussion section. So we will divide this part into three main subsections. We will start by giving the structural, mechanical, electronic, and magnetic properties of monodoped compounds with iron at different concentration in their bulk form. In the second part, we will fix the concentration at 12.5% and co-doped the monodoped compounds with alkali metals, namely lithium, sodium, and potassium, and further calculate their optical and thermoelectric properties. And finally, we will reduce the dimension of the monodoped compounds and calculate their structural, electronic, and magnetic properties. We start by the structural properties of the monodoped compounds in their bulk form. So we have varied the interval of concentration from 12.5% to 75%. We use it to do so the FP-LaPW based VNTK, the PBE approximation, the PBE plus MBG for gap correction. We have constructed 2x2x2 supercell type FCC and use it 4x4x4 gap points. As a first step, we have optimized the structures using the Birch-Monega equation of states into three main configurations, namely ferromagnetic, antiferromagnetic, and non-magnetic states. And the changes in total energy with volume for all the compounds are given in figure 1, in which it is evident that all the compounds are stable in the ferromagnetic states since it shows the lowest energy. In this stable phase, we have calculated the lattice parameter, the bulk modulus, and the formation energy for all the compounds, and illustrated the results in table 1. In this table, it is evident that our values are underestimated compared to experimental values, which is due to the well-known trend of the DFT. However, they are in good agreement with other theoretical parameters. The latest parameter is found to be decreased with increasing concentration. The bulk modulus is found to be decreased with increasing concentration, and the formation energy values are all negative, indicating their thermodynamic stability. In the next step, we have looked intensively into mechanical properties of the doped compounds, and the results are given in table 2, in which it is evident that all the compounds are mechanically stable since their elastic parameters conforms well with the Born criteria for mechanical stability. The bulk modulus, shear modulus, and Young modulus also show hardness and stiffness due to their largest values. The bulk to shear modulus shows that the binary SRS is ductile, whereas all the monodoped compounds are brittle. The ratio, Poisson's ratio, indicates that SRS has equivalent character, whereas all the doped compounds has an ionic character. We have further calculated the thermal properties in terms of divide temperature and melting points, and we have found good results indicating the stability of our compounds at high temperatures. Also, we looked intensively into anisotropy of our compounds by plotting their directional dependencies for bulk, shear, and Young modulus. The bulk modulus is found to be, or shows the perfect spherical shape, indicating its isotropy, whereas the shear and Young's modulus also shows or deviates from the spherical shape, indicating their anisotropy, which became harder with increasing concentration. The electronic properties are calculated in terms of band structures, total and partial densities of states. From this figure, it is evident that the binary SRS has an indirect wide band gap in the gamma X direction. After doping iron, the behavior transition to half metallic ferromagnetic with direct band gap for 12.5% iron and indirect band gap for 25-50% iron and a metallic gap for 75% iron. This behavior is also confirmed by their total and partial densities of states in which there is no state intersect the Fermi level in the majority spin, whereas the 3D EG states intersect the Fermi level in the minority spin, leaving the half metallic ferromagnetic character with 100% spin polarization. This character is also the results of the PD hybridization between P states of anions and D states of iron dopant. In the second, also we have calculated two important parameters, namely the half metallic band gap and the polarization, and the results are given in table 3. The half metallic band gap show good results for the half metallic compounds, whereas the polarization shows unity for the half metallic compounds and deviates slight from the half metallic for the 75% iron, indicating its metallic character. The magnetic properties are calculated in terms of magnetic moment and exchange constants. The magnetic moments are found to be an integer value of 4 Bohr magneton, which conforms well with the spin splitting energy and the Hund's rule. The most contribution to this value comes from iron and interstitial sites, whereas due to PD hybridization, local magnetic moments are created on the non-magnetic side of strontium and sulfide. Also, the exchange constants are calculated using these two formulas. The exchange constant between S and D states are found to be negative, indicating their antiferromagnetic interaction, whereas between the P and D states gathers both the positive and negative signs, indicating their antiferromagnetic and ferromagnetic interaction respectively. In the second part of our presentation, we have fixed the concentration at 12.5% iron and co-doped the monodoped compounds with alkali metals, namely lithium, sodium, and potassium. Since our work is based on the prior work, so we have used the same parameters, only we have enlarged the supercell to englobe 32 atoms. An illustration of the cubic structure and the total energy and cell volume for the co-doped compounds are given in figure 5, and the results are tabulated in table 4, in which it is evident that compared to the monodoped compounds, there is an increase in the lattice parameter, a decrease in the bulk modulus. The energy formation are also negative, indicating their thermodynamic stability. The difference between energy are all negative, are positive, indicating the stability of the ferromagnetic state, and the Curie temperature are also found higher than room temperature, indicating their suitability for spintronic applications. Interestingly, after co-doping alkali metals, the character transition from half metallic ferromagnetic to half semiconductor, with a direct wide band gap in the majority spin and a minor indirect band gap in the minority spin. This is also confirmed by their total and partial densities of states, since no states intersect the Fermi level, showing the half semiconductor character, which is also the result of the SPD hybridization. We have also calculated the bounding contour of electron density charge to determine their character. From figure 7, it is evident that all the co-doped compounds are ionic in character, since no overlaps is found between the orbitals. Also, in terms of magnetic properties, we have calculated the magnetic moments and exchange constants. The magnetic moments show an enhancement compared to the monodoped compounds, which is a good result, and also the most contribution comes from iron and alkali interstitial sites, whereas due to the SPD hybridization, local magnetic moments are created on the non-magnetic sites. In terms of exchange consonants, the SD exchange is found to be antiferromagnetic, whereas the PD exchange is found to be ferromagnetic. Since our compounds are semiconductors, so we were interested in calculating their optical properties. As it is known, electromagnetic radiation or the macroscopic response can be determined by calculating the complex dielectric function, which gathers the real part that indicates polarizability and imaginary part that indicate the absorption, and could be first determined by using the band structures. Once epsilon 2 is determined, epsilon 1 could be easily determined by solving the Kramers-Kronig equations. And once epsilon 1 is determined, all other optical properties could be found. In figure 8, we illustrate the real and imaginary parts of the complex dielectric function, the absorption coefficient, and the optical conductivity for the n-doped, monodoped, and codoped compounds. The real part of the codoped compounds shows a good enhancement compared to its Poisson, since it shows the highest static dielectric function, whereas for the monodoped compounds it shows negative values indicating its metallic character in this region and its reflectivity. The imaginary part of the complex dielectric function shows a redshift compared to the Poisson, and new sharp peaks are created in the visible to infrared region, indicating the application of our compounds as solar cells. The absorption coefficient and optical conductivity also shows high values in the UV region, also indicating their applicability in optoelectronic devices. Before delving into the thermoelectric properties, here we give a brief view on the thermoelectric materials. So thermoelectric materials are a category of materials that have the ability to generate an electric field in the presence of a temperature gradient. So through the Seebeck effect, different parameters could be determined, such as the Seebeck coefficient, electrical conductivity, and thermal conductivity. All of these parameters could be used to determine and evaluate the thermoelectric performance of our materials by calculating two important parameters, namely the power factor and the figure of merit. We should keep in mind that a preferable thermoelectric material should have high Seebeck coefficient, high electrical conductivity, low thermal conductivity, and so that figure of merit is higher than unity. The thermoelectric parameters are calculated or in terms of Seebeck coefficient, electrical conductivity, and electronic thermal conductivity are calculated using the Bolt-Strap 2 code based on the Boltzmann transport equations. The latest vibration of the system is determined using the slack equation, and the relaxation time is determined using the deformation potential theory. The results are given in figure 9. On the right side, we have illustrated the relaxation times that show the same variation for all the compounds, since it decreases with increasing concentration. And interestingly, the relaxation time for holes is 10 times higher than that of electrons. On the right side, on the left side, since our p-type values show good results compared to their n-type, so we have only illustrated the p-types, and interestingly, the figure of merit shows enhanced values reaching 3.5 for all the codoped compounds, indicating the applicability of our compounds in thermoelectric application at high temperatures. In the last part of our study, we have reduced the dimension of the monolayers of the monodoped compounds, and to do so, we have used pseudopotential based VASP, the PBE approximation, the HEC for gap correction, and a vacuum spacing of 20 angstrom. From figure 10, it is evident that the binary SRS is stable in the hexagonal structure, whereas the iron sulfate is stable in the square structure. Both the compounds are dynamically stable, evident from their phonon dispersion curves, since no imaginary parts is found. Also, they are thermally stable, evident from their ab initio molecular dynamic simulations, since the energy shows the same fluctuation during the time step calculation. Also, both the compounds are mechanically stable, evident from their elastic constants, which conforms well with the Born criteria for mechanical stability. The latest parameter after doping iron is found to be decreased with increasing concentration, and all the compounds show negative values for formation energy, indicating their thermodynamic stability. Also, interestingly, after reducing the dimension, the character transitioned from half metallic ferromagnetic to half semiconductor within the pristine iron as having the metallic character. This is also confirmed by their densities of states, which is also the result of the PD hybridization near the Fermi level. Also, in table 7, we compared the values of the total gaps between BBE and HEC and calculated the Bader charge to determine the transfer between the iron, strontium, and doped elements. Also, in terms of magnetic properties, we calculated the magnetic moments that shows an integer values which is comparable with its bulk form. We have come to a conclusion for our presentation. So, in the aim of obtaining new materials that are applicable for spintronics, spincalectronics, and optoelectronics, we have chosen the binary SRS from group 2,6 family and used different processes to do so. So, as a first step, we have used dopage with iron at different concentration and calculated the structural, mechanical, electronic, and magnetic properties in their bulk form. We have found that by doping the host SRS, we were able to change the character and enhancing the magnetic properties, making this compound applicable for spintronics. In a second step, we have fixed the concentration at 12.5% iron and co-doped the monodoped compounds with alkali metals, namely lithium, sodium, and potassium. We have found that by co-doping the single doped matrix, we were able to change the electronic character and hence making the compounds ideal for spintronics, solar cells application, and thermoelectric devices. And finally, as a last step, we have reduced the dimension and calculated the structural, electronic, and magnetic properties of the monodoped compounds at different concentration. We have found that by reducing the dimension, we were capable of changing the electronic character compared to their bulk counterparts from half metallic to half semiconductor. As perspectives, we plan to calculate the optical and thermoelectric properties of the monolayers to enable a comprehensive comparison between the 2D and 3D scales, and it will be interesting to evaluate the reliability of other methods such as inducing effects or external stimuli in S-based DMSs. Some references used in this presentation. I will be glad to answer your questions, and thank you so much for your kind attention.